Hi everyone, this is our second lecture about the mathematics behind the coronavirus or COVID-19. I had a first lecture and the reason for this is kind of understand the mathematics that's behind the coronavirus. So I made separate parts because I want to go over this very slowly so we can all understand. And as I told you, this is an SIR model and it's a deterministic mathematical model. And we know in each city we have three compartments right now. One are the susceptible people who can catch the disease, and one are the other compartment are the infected people, and the other one are the removed one. Removed ones are the recovered, and they can be recovered or they can die, which, as I told you in the first lecture, we don't want that. In the first lecture, I talked about the exponential growth and decay, and in this lecture, I want to talk about the algebra part. So the first lecture was also algebra and arithmetic, but we want to get into algebra, see what happens in a daily basis to this susceptible, infected, and removed population. Not to forget, if it's a city, S plus I plus R, susceptibles plus infected plus recovered people presents the population of that city or the world. So you can make it simpler and just say, talk about a city. Question, what happens to SIR on a daily basis? Now, the mathematical notation, if you go to one day to the next one, that basically you go from t to t plus 1, that's how we write it. And you want to calculate the difference of those three susceptibles, infected, and removed one on one day. To make it easy, I just called Monday and Tuesday so we can all understand. What happens when we go from Monday to Tuesday? Let's say we have 2,000 susceptible people on Monday. Of course, that 2,000 people on Tuesday, we're gonna have less people. Let's say 1,000 of them are infected, and on Tuesday we're gonna have 1,000 people. So usually when you take the difference, you do the S of Tuesday minus S of Monday. So we had, on Tuesday we have 1,000 people minus the initial one, which was on Monday 2,000 people, and that's negative 1,000. I want you to kind of note that negative sign. I put negative. And when you subtract in mathematics, we call that delta S, difference in S. So that's the notation. It's negative because it's decreasing. If we had 2,000 people on Monday, on Tuesday we have 1,000. So the number of susceptible people, it goes down. So that's something to notice, and I'll let you know in the next lecture why it's important to know. So if I calculate the average rate at which S changes per day, I can just say S of Tuesday minus S of Monday divided by 1 day. We all know from Monday to Tuesday is 1 day. And that's negative 1,000 over 1, or negative 1,000 people per day. And it's negative because it's decreasing. So now before going to I went to R. And same thing, R of Monday, let's say recovered people, we have no recovered people on Monday because that's the initial population of those three compartments. So on Tuesday, 50 people recovered. That means 50 people go from here to here. So let's calculate the difference. So here R of Tuesday minus R of Monday is 50 minus 0. And again, we call that delta R. That's a mathematical notation. And that's 50. Notice I put the positive sign because that is positive. If I want to calculate the rate, same way as I did there, R of Tuesday minus R of Monday divided by 1 day is 50 people per day, and that number is positive because the removed people are increasing in size. So another way you can write that mathematically, you can say delta R over delta T is greater than 0, so it's a positive number. And here I didn't mention, but delta S over delta T is a negative number. And that's one reason I'm going to get to the calculus part, and I'm sure some of you already know. So this, we say this rate is, this is the instantaneous rate of change, is negative. And here, that's why it's positive. So the negative sign comes from there because the number of people are decreasing. Let's take a look at the infected people in 1 day. On Monday, we have 100 people in the infected department or compartment. On Tuesday, we know that 1,000 people are infected. So that number is 1,100. But minus 50, why? Because 50 of those infected ones are recovered already on Tuesday. So if I subtract, we get 1,050. Let's look at it another way. If I write delta I, we all know by now what delta I is. It's 2,000 minus 1,000, which was the susceptible people, or S of Monday, minus S of Tuesday. So that's delta S minus 0 minus 50, and this was delta R. So from here to here. So if I write, I get 1,000. Again, negative times negative is positive, so we get same number, 1,050. Why did I do that? Because I want you to notice the difference in I is depending on the difference in S and difference in R. So you put delta S minus delta R. Same way, the rate, you just divide it by time, and that's what you get. This number is positive right now, but it could be also negative. Now, here I put the note, I'm going to come back to this next time. I said if it's negative, then it's good. If it's positive, then that's bad, because people are getting infected, and that's what's going on right now. Basically, this is when we have exponential decay, and that's when we have exponential growth. The goal is to make this rate negative, so that's how we can save people. So just you can watch this couple of times to understand the sign, negative, positive. On my next lecture, I'm going to talk about how we get that. So we're going to get more into calculus, and probably more a little bit more complicated lecture, but the final results are going to be very interesting. One more time, to get this rate positive, what we need to do is what they tell us to do: stay home, social distancing, washing hands, and you'll see why these are important. For now, I'm going to stop today. Please, if you haven't seen my last lecture, watch it and watch this one, because next it's becoming more interesting. Thank you for watching. Be safe and have a great day.